Okay, so this time we're going to talk about some classic distance problems. So remember, this goes back to the whole distance equals rate times time. So it's the same idea, but this time they're pretty classic in terms of distance. So in this problem, we have Leah driving from her apartment to her parents' house for the weekend. So driving to their house on Saturday, she was able to average 60 miles per hour because traffic was light. However, returning on Sunday night, she was able to average only 45 miles per hour on the same route because traffic was heavy. The drive on Sunday took her 1.5 hours longer than the drive on Saturday, and so our job is to come up with the distance between Leah's apartment and her parents' house. Okay, so I'm going to think about this in two cases. I'm going to think about the way to her parents' house. And this was her trip on Saturday. So I'm just going to use my distance equals rate times time. So I don't know the distance, that's what we're supposed to be finding. I do know her rate was 60 miles per hour, and I really don't know much about the time. So let me define some variables real quick. So D is the distance between places. And T is the time to her parents' house. So this is kind of her Saturday time. Okay, now I also know something about on her way home. So this is her Sunday trip. I know the distance is the same, right? The distance to her parents' house is the same as the way back. I know that she was only able to go 45 miles per hour because of the traffic. And I know that it took her 1.5 hours longer. So I'm going to call this T plus 1.5 because it took 1.5 hours longer. So I defined T to be time to her parents' house. So on the way back, it was 1.5 hours longer. Okay, so I have these two equations. They're both equal to the exact same distance. So we can just go ahead and set these two equal to each other. And do some algebra and solve, and we get that time is 4.5 hours. Okay, so that helps us. Remember, we're supposed to be finding distance. So once I know the distance, I can go ahead and substitute it in there. I could put it in the second equation also, it doesn't really matter. And so I find the distance between her parents' house and her apartment is 270 miles. Okay, remember there's lots of ways to look at these, so this is just one option. Sometimes you'll see people who will set up kind of similar equations, but they might do the way to her parents' house as T minus 1.5, and then on the way home they might just call this T, and in this case they've defined T to be the time back. Right, so it doesn't really matter where I put the T as long as I account for the extra 1.5 hours somewhere. And so there's no one right way. You just want to make sure somewhere you account for the 1.5 hours. Okay, so pretty classic here, this distance equals rate times time. So I want to look at a couple more where it's more about the solving is a little bit different. The setup is probably about the same. So if you feel really good with that, maybe you can be done, or maybe you just want to watch one more question, but I just want to look at some different options here. So here's another one. Kelly's boat goes 12 miles per hour. Our job is to find the rate of the current of the river if she can go 6 miles upstream in the same amount of time she can go 10 miles downstream. Okay, so think about this for a second. The boat can go a speed, in this case 12 miles per hour, but the current of the river is either helping or hurting that. It's either speeding up the boat or slowing down the boat, depending on which way we're going. So that's what they're asking us for, like, how is the current impacting really the rate of the boat? So I'm going to think about her upstream. So it tells me she can go upstream for 6 miles. And if you're going upstream, the water is going against you. You have to work harder. By the way, I'm still using this distance equals rate times time. So the rate, I know she's going at least this 12 miles per hour, but the river is making them go slower. So I'm going to do 12 minus C, where C is the rate of the current. And that's what we're trying to find. So I hope that makes sense. The boat can go 12 miles per hour, but the current is kind of pushing it back a little bit. And then times time, and we don't actually know what the time is, but they tell us that it's the same amount of time, so t can just be the time. Okay, when she goes downstream, she can go 10 miles, so that's right there. Okay, this time when she's going downstream, we've got the boat speed of 12 miles per hour, but then the current is pushing it, so the boat is actually going faster. So I have the 12 miles per hour plus the rate of the current, and then times the time. Okay, so in the last problem I could set the two distances equal to each other, but in this case the distances are not equal to each other. It's the times that are equal. So it would be really nice if we knew the time of the upstream and the time of the downstream and then set those equal to each other. So why don't we just do a little bit of algebra here. So the time upstream is going to be 6 over 12 minus c, and downstream will be 10 over 12 plus c. So there's our two equations for time, and remember it's the same amount of time. So we can go ahead and just set these equal to each other. Okay, so this is a proportion. It really makes sense just to cross multiply here. I'm going to be consistent and do this the way I've been doing all the other ones, but I think cross multiplying is probably the best option since it's a proportion. Looks like c can't be plus or minus 12. So I'm going to go ahead and multiply both sides by 12 minus c, 12 plus c, and again I'm just trying to be consistent here. So just multiplying everything by the LCM. So we lose these and we lose these. And we'll do some algebra. Hopefully once you're there you see that's an algebra problem you can solve pretty easily. And so we end up with c being 3 miles per hour. And remember that's what they were asking for, the rate of the current. So the current in this situation is going 3 miles per hour. So you want to think about like what's the same, what can I set equal to each other, and go from there. So I think I'm going to skip 5 because it's a pretty similar question, and I'm gonna look at 6. So this one says, at O'Hare International Airport, Cheryl and Bill are walking to the gate, and notice they're walking at the same speed to catch their flight to Akron, Ohio. And since Bill wants a window seat, he steps on the moving sidewalk and continues to walk, while Cheryl uses the stationary sidewalk, meaning she's just walking on the normal ground. So the sidewalk moves at 1 meter per second, and Bill saves 50 seconds by covering the 300 meter distance. So what is their walking speed? Which, remember, what is the same. By the way, if you're wondering, for some airlines, the sooner you check in, the sooner you can get on the plane and therefore pick your seat. Maybe that's how he's going to get the window seat. For some airlines, your seat is assigned to you, and it doesn't matter when you get there. You're going to get the middle seat or the aisle no matter what. Okay, so I'm going to use my distance equals rate times time again. So let's talk about Cheryl. So what do we know about her? We know it's a 300 meter distance, so that's her distance. We don't know their rate, that's what we're trying to find. Remember, this is for both of them, they have the same rate. And we don't really know anything about her time, so I'm just going to go ahead and call her time t. Okay, then we've got Bill, and Bill is going the same distance. His rate now is 1 meter per second faster, right? So he's got the rates, but then that moving sidewalk is helping him, so he's moving just a little bit faster. Okay, so I'm gonna do this. His time, he also gets there 50 seconds faster, so I'm gonna make his time, this is Cheryl's time, so time minus 50, right? T was Cheryl's time, and then minus 50. Okay, so this is one option here for a setup. So if I do this, I've got two variables, so it feels tricky on how I might solve it. So one option is to say, well, let me just solve this for a variable. So I'm going to maybe solve for time. So I'm going to have 300 over r is equal to t. And then I can just take that and substitute it in right there. So if I do that, I might actually multiply this out first. I don't know, for some reason that seems better to me. I don't know that it really matters. Right, and then I can put in my stuff for t. So I'd have r times 300 over r minus 50r plus 300 over r minus 50. Okay, so I can solve this thing. And I don't know, I'm going to try to simplify a little bit. So I'm going to subtract 300 on both sides. So now I have 0 equals negative 50r plus 300 over r minus 50. I don't know, I guess I can do this now. So the LCM looks like to be r, and r can't be 0. So I'm going to multiply everything by r. So I'm going to get 0 is equal to negative 50r squared plus 300 minus 50r. So I have a nice quadratic here. I'm going to turn this around. You guys know I don't like a negative out there. Let me erase that so we don't. I don't like this negative, so I'm going to move everything to the other side. So 50r squared plus 50r minus 300 equals 0. Okay, so I'm going to go ahead and solve this for r. So it looks like I have a GCF of 50, so I'm going to pull that out. So 300 divided by 50. Oops. I didn't actually pull the r out there. Okay, so 50r squared plus 50r minus 300. Okay, so I can go ahead and factor this. So it looks like I need a r, a 3 and a 2, and it looks like I need a plus 3 and a minus 2. So I end up with r equals negative 3 or r equals 2. And we can't be going a negative rate, so it looks like r equals 2. And that's what we were trying to find, right? The rate of both of them. And so there it is. They're going 2 meters per second. Okay, so one option there of solving. When I did this problem earlier, I actually solved this thing for r instead. And so I ended up solving for time and then had to substitute it back in. I'm going to throw out another option for you just to see some variety. I could have done it this way, where I have Cheryl is 300 times rate times time. I've got Bill, I could say he's 300, his rate still plus 1 because he's going faster. And then I could find his time also, but I'm going to call his time a little something. So I've got capital T as Cheryl's time, and I've got Bill's time as this. So I could also think about it like this. Cheryl's time, right? And then minus 50 seconds is equal to Bill's time. Or Bill's time plus 50 seconds is equal to Cheryl. So I could solve both of these for t. So we could have 300 over r is equal to t. So I could put that here. And Bill's time is 300 over r plus 1. So I could put that here. And then I could say, okay, our LCM is r times r plus 1. So multiply everything times r plus 1. And lose this here and this here, so we're left with 300 times r plus 1 minus 50r times r plus 1 equals 300r. Okay, check out what happens here. Okay, so I could subtract 300r on both sides. So I'm going to lose those. And, oops. Okay, right here, do you see that this should be a 50r squared? So this is 50r squared minus 50r. Got a little excited there, working. Okay, so I have negative 50r squared minus 50r plus 300 is equal to 0. And look, that was the same thing I had over here. So same thing, turn it around, we'll end up getting r equals 2. So it doesn't matter, I looked at the setup kind of two different ways. Over here, I thought about it in terms of time. And over here I kind of thought about it in terms of the two distances. And I got the same answer either way. So remember, there's a little bit of flexibility here. It's really key to think about this distance equals rate times time. Okay, so I'm wishing you good luck as you try the homework problems. You know, I'm happy to answer questions that you have. So hopefully this gives you a good kind of foundation, and then you can come ask some really good questions. We'll see you later.